Hello out there. Welcome to the Earth and Planetary Surface Processes section that we're now called, not a focus group. There are three things that we're going to do this afternoon. It is a business meeting. We have business to tell you about. We'll then celebrate the awardees of our section, and then we'll hear the sharp lecture from Jill Marshall. So let's begin. So here's who we are. And there's an executive committee of about 30 members, and there's an awards committee, there's a fellows committee, a student committee, a fall meetings program committee, and a web page, social media, and fundraising committee. And we met this morning, and we've added a few more committees. So, because that's what you do when you get together in a meeting. And actually, our group is distinguished by being relatively organized, and so we have a centennial committee, we have committees on various things that we think can interact effectively with this thing called AGU to effectively get things accomplished that we want. And so I want to thank all the members of the executive committee who are in some way or another taking a leadership role in doing that. Some numbers. The black numbers are last year, the red numbers are this year in terms of who we are. That is, our current number of primary, their primary affiliation is 2219, and secondary is 8398. So we've grown, and I wasn't able to get from the staff here the breakdown between student and regular, but it's probably pretty similar. And AGU now has 25 sections. It's really grown. But in that, we're the 10th largest by primary and the 6th largest by total affiliations. And we have a presence that's noticed in part because we're organized and by the work of Jim Pizzuto and Alan Howard and now Dorothy and Gordon, who are, let's say, more socially able than I am, that they're getting, they know we're here, and it's good. AGU appreciates us, and they're helping us make us be a successful section. Please note the following. AGU has a matching grant in which if we can get 5% of our membership to donate at least $50, we will receive a match of $1,000. And it actually goes up. If some miraculous way we get 7%, we get $2,000. And 10%, which is hard to imagine, we could get $3,000. Last year we did not get there. We need to get about 60 individuals to contribute. So if you're thinking you could skip 4 lattes and make a contribution, that's the cost of a latte in Berkeley, then make a contribution because it adds up. And we are, we have more than $1,000 in the bank, but not a lot more. And what does that money that we get in donations do? Well, it improves your experience here either through receptions, travel grants, and aids to students. So it makes us do the section more vibrant. And this is what it says. Now, there's another special thing. I don't know if Dorothy wants us to add to this by saying a few things other than what she's worked with Joel and others to have this fabulous tumblers. And I understand it's made out of platinum and zircon. They're about $100 each. Is that right?
I would say you can't buy them fast enough. They're just flying out of the boxes here, so you better scramble. Joel, were you in the room? Joel? And what do you want to say, Joel? Tell them how to get them from you.
You can come back after the sharp lecture ends. We'll be happy to sell you some. If there's any left, we'll have them at the DPF mixer tonight, and then here we're fun. But better if you buy them right now after Jill's lecture, because otherwise I have to take Gary lunch to the mixer and then dinner to guys.
What's the price, Joel?
They're $20 per student and $25 for everyone else. And all the money goes to support the student travel band and the year night.
Okay. So this is symbolic in many ways. One, of course, is symbolic of Gilbert and his ways and means. It's also symbolic of the commitment and enthusiasm that our section has to encourage participation and make this a vibrant meeting for us all. So thank you, Joel and others, for making this happen. I want to also give thanks to a few major committees, which is the Fall Meeting Program Committee led by Kimberly Hill and then contributed by Greg Hancock, Marissa Palusis, and Giovanna Coco. And Kimberly, I've asked if she will say a few things about this, because this is the person who has been our rudder in navigating the choppy waters of figuring out where our sessions will go, the timing, to make it go well. And she's done a great job this year, so thank you.
Thank you so much. I just want to say it's been a really rewarding experience serving on the program committee. It's a fun experience to learn the inner workings of AGU. You get kind of exposed to the different things. And I'm saying that because I feel like we benefit when more and more of the community is involved, at least in some way, in the program committee, whether you're submitting sessions or submitting abstracts or actually serving on the program committee. So I want to say we really want your feedback about how the program is evolving. Bill mentioned that our EPSP is getting bigger. That means we have more sessions proposed and more abstracts proposed. So we're trying to think about how to manage this best so that it's a really great experience for everyone involved, students, full professors, everyone coming from companies. So I really, I want to invite you, I'm going to take this opportunity to invite you to give me feedback that I can feed to the rest of the community, or give Bill feedback if you don't want me to know who you are, who's displeased with something. Or you can, if you want to serve on the program committee, we would really love to hear from you. So thank you for all the community who has been involved to this point, and I hope to hear from you soon. Thanks. Thanks, Ben.
Thank you. It really is a big task, and I appreciate all the effort made there. Another committee that's been active this week, is the Outstanding Student Presentation Award coordinators and liaisons. And we thank all of these individuals for taking the time and finding the time and avoiding the bumping into each other and not getting to the student presentations, so we can acknowledge and recognize the good work that our students are doing. So thank you to this committee as well. So thank you all for that. Okay, a little more data. This year we had 42 oral sessions, 30 poster sessions, and 991 abstracts, which is pretty good. I mean, in terms of primary affiliations and talks, it's nearly half. So if we count it that way, so that's a good sign. Another sign is Gilbert Club. Monghan Huang and Karin Prestegard have led that, and there is still time. Some of us have said, can I still do this? And the answer is yes, you can. And I'll remind you of our lineup this year of Cliff Reby, who will talk about rock, water, life, and death in Sierra Nevada forests, and many other things. Justin Lawrence from NSF will give us an update and status of geomorphology and land use dynamics. Paula Pasagua will talk about the tales of two river systems, and Christian Franz Leonard will talk about modern and neogene erosion in the Mayas. John Buffington will talk about the status of JGR surface, and then, of course, there are the great pop-ups. So if you forgot to sign up or don't know what this is and want to come, it's still possible. You can go to the EPSP webpage, or is Monghan here? He was going to try to make it. There's Monghan, and he's taking the responsibility, and Karin's over there. I didn't see you, Karin. Come here if you want to say it loudly. I think you can do them all. Yeah. Can you, so at the end, can you see either of them to get their names so they can get a full accounting? That's great. Anything else, Monghan?
There will be a bus there between 8 and 10 a.m. at the College Park Metro Station. So when you get into the College Park Metro Station, just look for the bus that has a Gilbert Club sign.
So the bus will have a Gilbert Club sign on it? Okay, great. Okay. Let's see. Right. Okay. Now I have 4 announcements that come from our experience with AGU and the AGU Council. First is that in 2019 is the AGU Centennial, and the AGU is seeking creative ideas to celebrate and to celebrate. So we haven't done it yet, but there will be a link on the EPSP webpage for proposals to come in. And Gordon wanted to take this opportunity. Yes, still Gordon? Yes. He's got a microphone in front of him, and you know what's going to happen next.
So this is just sort of an effort to salt the mind a little bit. One kind of idea that, I mean, they're very enthusiastic and they want lots of ideas. One idea that I had, I think I even threw to my, why I want to be president for some silly reason, statement was a disaster film festival. And it seemed like a way to bring people into our field, since disasters are really, science and geomorphology in action. And so the concept would be to curate a set of high-level videos that illustrate, key processes, key disasters, have them narrated, possibly have them compared against their Hollywood versions, And I think we could imagine this as a traveling exhibit. I mean, it's still somewhat unformed, but if you're interested, this is going to take an effort. I don't particularly want to lead it, but I'm happy to work with it. I know we all know how this is going to go, right? But if you're interested, let me know, and we'll figure something out. Thanks.
But it illustrates the range of thinking we're looking for. This is an opportunity, and AGU says that they'll provide resources for things that seem to communicate either well, expand other AGU participation, but also a lot of thought is being given to making science accessible to the public in one way or another. So we welcome your thoughts on this very much. The second is there's something called AGU Narratives, which is also part of the Centennial Plan, to illuminate the stories of sciences, celebrate the accomplishments in earth and space science, and reveal the personal and scientific stories of science. So we were asked to make some suggestions, and let me explain what happens with these. These are videos, and they will be made available, and the concept that AGU's got is that they're going to collect these videos and make them available through the web to perhaps inspire in very different ways, inspire people to come to science, inspire people to be excited about the science, and put people behind the data, if you like. And the three people who said yes and will be, have you been narrated already? I don't know. Not yet?
No, not yet.
Not yet, but you will be. You'll know when it happens. So we can do more. There's this for this meeting. This is this, but they want to make this sustaining. I don't know whether there'll be more at the next AGU or they'll do it in between. But there's an interest in, and this is another example of this AGU's centennial outreach. In case you missed it, this is the schedule for the coming years for where it's going to be. So in 2019 and 2020, the city in which I was born will be where it will be hosted. And then it will be New Orleans, Chicago, and then back to San Francisco, and you can see the rhythm that will be established. Every third year in San Francisco, every other years elsewhere, and I think I left 2025 off, which is DC again. We come back here in 2025. So as much as your memory cells can record your experience here, re-energize them in 2025 for where you got a good lunch and those sort of things. This is the plan. This is solid. This is what's going to happen. Okay. The fourth thing is from the prow, which refers, which I didn't know this, refers to the front of the AGU building there, which is ship-like. And AGU's building renovation is nearly done, and it's a zero-energy building. It's the first in this DC that they're, what's that? No, how can I say this right? Zero emissions, yeah. But also, yeah, just to stop there. Come see it. It's been renovated there, and they want people to use it as it becomes available. So if you're traveling through DC and have an opportunity to come to the building, but importantly, this is electronic communication from the prow where folks are invited to make statements. And a folk here, Dorothy Meritz, was asked to talk about World Soil Day And so she's written a statement about that, and I encourage you to look at it and maybe look with some frequency at the prow. Okay. A statement I'm here to tell you about is, and I think you've probably heard about this in 3 or 4 different ways now, because Lena Patino was handing out little cards to remind you. The NSF is really eager to hear from you. I'm on this committee that they've established, the Catalyzing Opportunities for Research. They've asked this committee to set priorities and strategies for investment in research, infrastructure, and training in the coming decade. And I will tell you, the 2 previous decadal surveys had consequences. The one that was, in fact, the 2001, the Bros report is called, is why there's a critical zone support. It invented the term to explain what we were doing. And through the wonderful leadership of Sue Brantley and with help from Suzanne Anderson, they made this a reality. And so these reports can shape our future. And if you have ideas that you think would be cool for a direction our field should be going, send them in. I'm going to be on the receiving end and accounting and recording and trying to synthesize this into representative questions from the community. And NSF will be looking at this response. They want to see excitement, enthusiasm, and ideas. So please take the time. There's already been something come out on the through Gilbert Club directly from Justin Lawrence, and if we can ever get a hold of our AGU EPS section list, you'll get reminded that way. So I know you probably heard this 3 times now, but NSF really wants to hear from you, and I encourage you to do it. Okay, so we're going to take a moment now and ask if there's any comments or questions, because we're nearing the end of the business part of the meeting, and I would like to know if there's anything that's someone in the committee has a question, concern, idea they want to express now. I know that most of you are going, but if you have something, please speak up. I mean, Doug, what are you going to say?
Helen's not here. I'm on the Fellows Committee. Just like the Awards Committee, we need nominations.
Yes.
So we always come out at a certain time of year and try and scare them up, but you also need to and should come to us. So Helen's the one that's in charge of the Fellows Committee. I'm also on it. Bob's on it. I don't remember who else is on it.
I'm retiring onto it.
There you go. And so fellows and awards, we need as many as we can, right? And we've been pretty good.
Yes.
Our fellows, we've been pretty successful with them. So we know how to help craft the packages, okay? But we need them from you. No one can get them if they're not nominated.
And I'll add, I didn't know this until the council meeting on Sunday. AGU tracks this. They want to see, and in fact, Dorothy documented the fellows and the awards nomination procedure this year, and it was posted and presented at the AGU Council as exemplary effort. So please do think of your neighbors, your friends, people you know or that you feel are due, and make the effort to communicate your desire for one of the awards. And on that note, wait, let me stop. That was a quick test, but Mike was asleep. He didn't notice. Are there any other announcements, thoughts, or statements? This is our community time to say something if someone wants to. Do you want to say something more, Doug? Okay. All right. Anybody else? All right. Then let's go to this, which I think we're a young enough organization. We need to thank and acknowledge the founder of this organization. He's here. I made sure he was here. Mike is part of the reason we exist. He advocated for this. He made a case for it being a separate entity from hydrology, and got it going. And I want to thank Mike right now. Thank you. Okay, and then there was a succession of frightened people who followed him. Alan Howard and Jim Pizzuto, me, and your new president, to come within a few minutes is Dorothy Meritz, and then comes Gordon Grant. Something to look forward to. Okay, and now we're moving to the celebratory part of this. And of course, we want to celebrate our new AGU fellows. The strange poster-looking things, if you look closely, there are people there. Was this last night? Is today Thursday? I don't know. These are pictures I took on my cell phone as they were marching up to be celebrated. So Friedhelm and Heidi and Josh and David and Timothy, congratulations to all of you. And as Doug said, please keep making nominations. We compete well because we are good. After this lecture, after the Sharp lecture, there will be a reception at the Grand Hyatt, and it's ticketed, but we're not supposed to, Next year won't be so irritating. We just had a meeting, and we're trying to prevent this wall that got set up on day one. So we'll see you over there. And, bring your tumbler. Okay. Now, we're moving to the awards. And first to explain the awards, and then we'll introduce the presenter and the awardee. So the G.K. Gilbert Award in Service Processes, it says, in recognition of sustained and outstanding contributions to Earth and planetary service processes, and as someone who has also promoted an environment of unselfish cooperation in research and inclusion of young science into the field. It's very broadly defined. It really doesn't have an age distinction or any other distinction. It's a person that you see who makes these, fits both of these goals of outstanding contribution and unselfish cooperation. And appropriately, our winner this year. So we asked Paula to come up and make a presentation about the award.
Thanks, Bill, and good afternoon, everyone. My name is Paola Passalacqua. I'm an associate professor at the University of Texas at Austin, and it is my greatest honor to be introducing Professor Ellen Wall as the recipient of the G.K. Gilbert Award this year. And I have a second honor, which is the one of representing two wonderful colleagues of mine, which are Nicole Gasparini at Tulane University and Elwin Yeager at the University of Idaho. The three of us wrote the citation for Ellen together, which is what I will read. Professor Ellen Wall fully represents all of the qualities of an inspiring and groundbreaking scientist. She has consistently and significantly advanced our understanding of processes in numerous subfields in geomorphology. Ellen has more than 200 refereed publications, with many being in key geomorphology journals, and these publications have made tremendous contributions to understanding the morphology, sediment transport, wood dynamics, and hydraulics in steep mountain channels. Her work has also greatly advanced the understanding of carbon storage and transport in rivers. Ellen has also worked to incorporate fundamental research into the more applied work of river restoration. Through this work, including 8 books for non-academic audiences, she has had a large impact on helping both scientific and non-scientific communities outside of geomorphology understand the importance and practical application and knowledge in our field. Ellen has effectively supervised and graduated over 70 PhD and master students. Most of these students have gone on to lead successful careers in academia and government science, thereby further influencing knowledge in geomorphology. Ellen is consistently a fair and extremely supportive colleague for everyone in geomorphology. She has served as a role model to countless female geomorphologists, as a direct mentor or collaborator, an indirect mentor at meetings, and by being one of the few female full professors in our field. While Nicole, Elwin, and I have not worked directly with Ellen, she has provided all of us inspiration in terms of her scientific excellence and continual inclusiveness of young scientists. Ellen's compassion for her community would be remarkable, even if she was not one of the elite researchers in our field. We know of no other scientist in geomorphology who so truly excels in both science and community engagement. Everyone, please join me in congratulating the 2018 G.K. Bieglert Award recipient, Professor Ellen Wall.
Thank you all very much. I'm very honored to receive this award. I know there are many people in our community who are very deserving. And as Paula indicated, as the first female scientist and a female scientist in the time of the Me Too movement, I'd like to say a few things about mentorship. And I should say, I truncated that, the first female scientist to win this award. That's what I meant to say. I'm not Eve. I am very fortunate that I have never experienced anything that the Me Too movement has arisen to protest. On the contrary, I've been extraordinarily lucky. My professional career and my life have been shaped by many extraordinary mentors. I have to start with my father and mother, who were, my father was a science teacher and my mother was a librarian, and they really introduced me to science and the natural world, and I think fostered a lifelong passion for both. They also encouraged me to be physically strong and not be afraid, but to be active and confident in the outdoors, and that's been very useful as a field scientist. So I also had an extremely strong education in the public school system, and when I started as an undergraduate and a geology major at Arizona State University, I really had a succession of excellent teachers. They very much emphasized field-based learning. They pushed me to do as much as I possibly could. They introduced me to research via extra class projects, a senior thesis, and then I'd say this trajectory continued when I went to the University of Arizona. And I was really fortunate to work with Vic Baker, who I know is here tonight. And Vic and Bill Bull established just an extraordinary atmosphere for the graduate students in surface processes at the University of Arizona. It was an amazing atmosphere, and I don't use the word amazing lightly. It was a group that included Lisa Ely, Dorothy Meritz, Jim O'Connor, Sarah Rathburn, and I think at the time we all knew that we were part of a very uniquely supportive and intellectually stimulating research group, but I didn't really fully appreciate that situation until later, when I began to know other people in our community who had had very different experiences when they were graduate students. So in addition to the positive mentoring, I just want to briefly describe one other thing. We're all shaped by a variety of life experiences as we go along, and one example that has stuck in my mind for a very long time was my 7th grade geography teacher, Miss Paget. That was the only name I knew her by as a student. But one day she completely ignored a large group of the students in class. She wouldn't call on us. She gave absolutely no visual recognition that we existed. And I was kind of an eager student. I was used to being called on and acknowledged, and I left that class. This went on for the whole class period, and I was really hurt and angry. I couldn't understand what had happened, and she never said anything until the next class we met, and then she explained that she had deliberately ignored anyone in the class who had brown eyes. And then we talked about prejudice. So that experience really stuck with me, and I think, it's an example of what I'd say is that we can influence each other in positive or negative ways, sometimes without even being aware of our influence. And to be frank, I don't see the point of behaving in an arrogant or domineering fashion. People remember that about you, but not for the right reasons and not in a good way. And if you think about some of the individuals in our community whom people respect both for their intellectual contributions and they remember very fondly because they were good human beings who treated others with respect and fairness, two people come to mind for me, Stan Shum and Reds Woolman. They're ideal role models for how we can behave with each other and with the rest of the world. So I've been very lucky to have supportive, positive supervisors and senior colleagues, and they fulfill what I consider the definition of mentor as a guide and advisor. But I've also seen the opposite side. I've worked with people who have been damaged, sometimes for years, not just by lack of mentoring, but by harassment, whether the harassment is related to gender, race, or simply age or career stage. The harassment had nothing to do with intellect, ability, or work ethic. It was something that was irrelevant and certainly beyond the individual's control, like being born with brown eyes or simply being younger and earlier in your career stage. So I'm sure everybody in this room would agree there's no justification for overt harassment, and I think most people agree on that and don't do it. What's trickier for all of us is the ingrained attitudes. To some extent, to be human is commonly, unfortunately, to harbor some prejudices of which you might not even be aware. And we're probably all in that position, but we can also each try to be cognizant of those attitudes and consciously strive to treat others as fairly and supportively as possible. It's, the golden rule is ancient, but it's still very good advice. So because I was generously supported intellectually, emotionally, financially by my mentors throughout my education, I think it's been easier and natural for me to support my own students and younger colleagues. And to state the obvious, I've benefited tremendously from those interactions. When people feel safe and supported and valued, they give of themselves very openly and generously, and it's the ultimate reinforcing feedback. You gain from what they give you, as well as giving things to them. So we can all have our own positive feedback loops. So I'd like to just close by really thanking everyone who has helped me along in my career and allowed me to reach this point. And more importantly, to encourage everyone here tonight to not just meet what really should be a very low bar of not harassing or impeding others, but a higher and ultimately much more fun level of activity of actively encouraging and supporting others. When I was a grad student, I had a very dear friend who unfortunately was killed in a car accident while he was a grad student. His name was Keith Katzer. And he had a nice sense of humor, and he would talk about fairy godfathers and fairy godmothers. They were the senior people in your discipline who did good things for you, and we've all had them. The people who write letters of recommendation, who provide thorough, balanced, and constructive reviews of papers and proposals when you're just learning how to write papers and proposals, the people who establish scholarships or travel funds, or the people who simply provide an encouraging word and some perspective when the situation feels discouraging or overwhelming. And the last thing I'd say is no one is too junior to be a fairy godmother or fairy godfather. So my suggestion to each of you is that you first take the time to thank your fairy godparents, and then think about how you can strengthen the tradition and, to use a very bad metaphor, help turn what may be a pumpkin into a golden carriage for someone else. Thank you.
Why does it say okay? Anybody, do I hit okay? Hit return? Oh, thank you very much for your presentation. Now the Leopold Young Scientist Award, given annually to one career scientist. That could be read strangely. One early career scientist. No, I'm sorry. I've had 4 hours of sleep last night. No more than 5 years post-degree, in recognition of a significant and outstanding contribution that advances the field of Earth and planetary surface processes. Here's our winner. And Josh Ruring will present.
I had the distinct honor of, I said I wouldn't cry first, Jill. I had the pleasure of advising Jill for her PhD, and there's a lot of times during that experience where it wasn't clear who was training who. And I've had subsequently the pleasure of going back to some of her field areas and chatting with landowners and other people. And I always have to reintroduce myself. And I said, yeah, remember Jill Oh, Jill, yes, I remember. And not only do they remember her, they remember what she did. And I think that will continue to be the case. So I'm delighted to present Jill as the 2018 recipient of the Luna B. Leopold Award. She is a relentless scholar, a fearless scientist with contributions in soil geomorphology, paleoclimate and landscape evolution, modeling, topographic analysis, mechanics of biota. She is not afraid to do anything. From the outset of her career, she has demonstrated a mastery of the big picture stuff, as well as the details that need to happen to get the big picture questions investigated properly. She thrives on collaboration. Those of us fortunate to have been drawn into her scientific orbit have been incredibly blessed by this opportunity, and Jill is highly deserving of this award because, very much like Luna, she refuses to recognize the barriers that might otherwise separate theory from the field. That is her strength. For her MS degree with Leonard Sklar, Jill mined soil science data in ways that no one else had to demonstrate that climate can influence class size distributions, and that work is still being advanced today. We saw some of that this week. During her PhD, she challenged the notion of steady-state erosion in unglaciated landscapes and used a sedimentary archive to look at the coupling between paleo-environmental trends and paleo-erosion rates. And by combining those with some paleoclimate simulations and a frost weathering model, she highlighted the surprising extent of periglacial processes in unglaciated landscapes, and you're going to hear more about that today. More recently, Professor Marshall has tackled the problem of how tree roots penetrate, fracture, and extricate bedrock in near-surface environments. This is something you see in cartoons and textbooks quite a bit, but no one has touched this problem. Jill has taken it on. In summary, she is a shining example of the interdisciplinary and deeply skilled geoscientists that funding agencies and institutions seek to train and employ to solve pressing problems. And I'm excited to see her next set of discoveries and the directions that she defines for our field. It's my pleasure to introduce Jill Marshall.
Okay.
There's a little magic, because she's used the PC.
I'm going to go put my cup away before you steal it.
It worked. Come back.
Really? You're not done? Okay. Oh. Well, thank you, everyone. This is a spectacular honor, and I'll talk more about that. Oh, I didn't even figure out where my mouse is. I'm supposed to do that, huh? So I'll talk more about that in a second. Am I this keyboard? No, I think I'm this keyboard, Bill.
Oh, you're on that one? Okay.
Yeah, sorry. Sorry, just a momentary technical setup here.
Why don't you use a Mac?
Bill? I was going to really thank Bill, but I've changed my mind. All right.
And then there's the...
Okay. What thing?
Oh, you got two of them.
Okay, cool. Okay, let's get this show started. Okay, so I first met Luna Leopold at a seminal time in my life. I was invited to join a class of people in different disciplines who were working on rivers. So each one of us students represented a different discipline. I was the token geomorphologist. And at the time, as fish populations were crashing across the West, geomorphologists and botanists and engineers and hydrologists, we all struggled with what does it mean to be a river. And of course, Luna, in both field and theory, he was a scientist who covered broadly what does it mean to be a river.
So to have an opportunity to meet him, and he was one of the professors for this class, and to have an opportunity to meet him and to learn from him and other river people who came in on how hard it was to work across disciplines, but how much it mattered, was incredibly important. And so in a few moments, I'm going to read a quote from Luna's 1974 Horton lecture. But before I do, I'm going to paraphrase a story from that lecture. And so Luna describes in the paper on how he met another river scholar. And that river scientist, Dr. T. Stewart, was just as interested in rivers as Luna was. The difference is that Dr. T. Stewart cared about them because Dr. T. Stewart cared about the wee fish. And so Luna and Dr. Stewart discovered that the two of them had together independently discovered generalities about rivers. But there was one thing about a river that Dr. Stewart had discovered that Luna had never thought of, and that was subsurface flow in the gravels. Because subsurface flow in the gravels is so important for the fish eggs and the tiny fish as they're hatching and as they need to escape the winter flows that come down the river. And Luna writes in this talk that the minute that Dr. Stewart said this to him, he immediately understood the hydraulic reasons for the subsurface gravel flow. But it wasn't until he met someone with a different discipline who had a different focus that he himself could add that into his own view of the river. And that really resonates with me. And this quote, he went on to say this in the talk and in the paper from the talk, which so resonates with me. What he said is, what I wish here to stress is the relatively long gestation period that is often required for the emergence of a distinctly new idea. Its emergence, at all too often, is the result of two factors. First, continual thinking across disciplinary lines and the application of concepts from one field to a distinctly different one. And two, the continual admixture of practical work and application with theoretical and purely intellectual concerns. And number one, I am so profoundly and deeply honored to be nominated for this. I'm going to try not to cry, let alone to be a recipient of the award. And you'll see me talking about collaborations throughout my talk with so many mentors that I've had. I feel like Ellen, I've been very, very lucky with the mentors I've had, and it's a big community. But the reason that this particular quote from Luna resonates with me so much is this continual thinking across disciplinary lines and where that gets us as a community for the science. So what I'm going to talk about today are two broad topic areas. First, I'm going to focus on the role of ice, and as Josh said, in unglaciated terrains, and it all starts with Little Lake. And you'll hear more about Little Lake in a few slides, but Little Lake was a paleoarchive, and by the time we finished working there, we had sufficient evidence from several different lines of evidence for at least a 3 times increase in erosion rates due to frost cracking, which was quite a surprise to us. And so we went on to, as Josh mentioned, to look at paleoclimate models and couple them with frost cracking models to begin to ponder what the extent of frosty processes might be in unglaciated terrain. And then for the second half of the talk, I'm going to talk about trees. And I'm going to talk about using a novel technique and combining it with all of the wonderful infrastructure and people structure of the critical zone observatories to begin to try and parse this question of what are the mechanics of a tree's converting rock into soil. And I'll present some preliminary results on how to think about perhaps frequency and magnitude and the different ways that trees in different climates can break apart rock. And so essentially what I'm going to present to you today is a couple of broad topics with new ways of asking old questions with an admixture of disciplines. So if we travel back in time when the last great glacial, when much of the Earth was covered with great ice sheets, it's easy to see how climate expressed as a glacier that once lived in this valley, was able to modulate flux and form. You can see it, of course, in the U-shaped valleys. You can see it in the pile, the rubble of rock that was once bedrock and is now mobile material in that moraine at the forefront of the photo. But of course, if we go to someplace like this, to my beloved Oregon Coast Range, it's really difficult to discern any imprint of past climates, cold climates, in a landscape like this. And so this is a brief introduction to Little Lake, and I'll show you a few more details, but I wanted to give you a sense of the scenery. So this is an oblique view. All of this right here is the old Paleo Lake deposit. There's a landslide dam way back here. That circle is Little Lake. It's really little. And this is the watershed that we studied. The other thing you can see in this Google Earth image is the forested, deeply forested, very, very steep hills of the Oregon Coast Range. And this project, of course, was not just me, but an entire cast of wonderful people. So I'd like to introduce some of the players to you. Daryl Granger, many of you know, on the left. And on the right, Dan Gavin is a paleoecologist and biogeographer. And then Alan Rempel studies the mechanics of ice and pre-melted films. Pat Bartlin, who goes by Bart, so when you hear me refer to Bart later on in the talk, he is a paleoclimatologist, and working with him has totally changed my worldview on how, as a geomorphologist, we need to think about climate operating across the land. And then Josh Rohring, our newest fellow in class of 2018, and T.C. Hales, and then Dorothy Meritz. And while Dorothy didn't work on Little Lake, she and I have spent countless hours in the field and at the kitchen table talking about the extent of periglacial processes, and she has done much to shape and change my thinking. And just a shout out, if you're interested in this story of Little Lake, Josh is going to be talking about chemical weathering rates in conjunction with the physical weathering I'm going to talk about Friday. Okay, here we are at the well-studied Oregon Coast Range. I use this photo frequently. Al Hanwiger is now featured in all my students' posters. That's the roots of a Doug fir. It's what blankets the Oregon Coast Range today. And this is a place that has been, as many of you know, well-studied. It's a place where we know in the modern times that trees absolutely dominate sediment production. It's never been glaciated. It has a uniform ridge and valley topography, which suggests that the diffusive and advective processes have had time to equilibrate. The catchment average erosion rates in the remarkably uniform Tyee sandstone of the Oregon Coast Range average about 0.13 millimeters a year up and down the Coast Range. It's a place where erosion broadly balances rock uplift, and for this and many other reasons, it's been considered for many years to be an ideal steady-state topography, so much that you might consider it a test locality for geomorphic laws. It's a place where they were formulated, where they were parameterized, tested, and calibrated. So this is Little Lake. It's rotated, north is going this way. And this is a place where it's an awesome place, where we can try and discern mechanistic linkages between climate change and erosion rates. So rather than just saying climate, or saying it was wetter or drier, trying to actually get at the mechanics of what do we mean by that? How are you actually incising a river faster or breaking the hill slope down at faster or slower rates? The forefront is our primary sampling site. We had several others. This was an erosional, we were trying to get the sand size fraction, and so by getting the sand size fraction that we wanted for erosion rates, it did mean that we are missing part of the early Holocene, but the core chronology is intact. And then we also sampled from rivers to get modern day sediments high above the influence of the former Paleo Lake. Here's the landslide deposit in my awesome graphic skills that it's outlined with. Yeah, okay. I agree with you. If anyone wants to help me with my graphics, you're welcome to. Okay, so what's so great about Little Lake is that it spans 3 climate intervals. It spans the warmish marine isotope stage 3, the last glacial marine isotope stage 2, and the modern Holocene. It's a quiescent sedimentary environment. It's small, 6 square kilometers, which means that its processes are well constrained, and we have essentially direct hill slope to basin deposition. There is no place for storage in this watershed except at the edge of that lake. We have this has been well studied by paleoclimatologists, which means there was already a detailed climate history inferred from the pollen, and it's a single quartz-rich lithology, which means we can get millennial erosion rates from in situ beryllium-10. So this special place allows for coupling climate and ecosystems and erosion mechanisms and rates. So we cored down 63 meters and found some great things in the core, and I'm going to walk you through some of what we already knew about the paleoclimate inferred from the vegetation and some new findings. So starting on the right, going from top to bottom, during the marine isotope stage 3, it was open canopy forest and about 3 to 6 degrees less than modern and wetter than modern. During the glacial, it was a subalpine parkland. So that is like this figure up here. So very few trees, grasslands, very, very different than a forested setting. And mean temperature was about 0 degrees C, and it was drier, but not by much, about 25 to 50 centimeters less annually. And then, of course, we have the modern Holocene, which started in the pollen record at 13,000 years, the Doug fir were there. So it's a closed canopy forest. The mean annual temperature is about 11 degrees, and the mean annual precipitation is 1 to 2 meters. So we were able to find, starting about 30,000 years in the core, we found the co-occurrence of Sitka spruce and subalpine fir. And those 2 species only occupy a very, very narrow range. What they need is the influence of a marine setting and cold climate. So currently, they're only found in this part of the world and a couple other places, but they're found in southeast Alaska right here. So despite the fact that Little Lake is over 400 kilometers to the south of the maximum extent of the ice sheet, we know that starting about 29,000 years ago, 30,000 years ago, it was like southeast Alaska. And it's important to realize that that 29 to 30,000 year number is several thousand years before the official start of the last glacial maximum. So if you remember your sawtooth climate, glacial interglacial cycle map, it's cold and getting colder, then it shoots up warm, cold and getting colder, shoots up warm. So we're in that period when it's already getting cold. So this is the erosion rate data, and let me walk you through the plot. So the erosion rate derived from beryllium-10 is on the y-axis, and then this is starting 50,000 years ago and going forward to the present. These samples here with the open triangles, those were samples that were have age-reversed sediments. So there was fossils that were younger than the overlying fossils. So this is the marine isotope stage 3, and starting about 50,000 years ago, erosion rates are 0.06 millimeters a year. And then as we're going from a temperate to montane to subalpine climate, there's a 3 times increase in erosion rates. And then during the last glacial, erosion rates stayed, as we had the subalpine landscape, the erosion rates stayed steady at about 0.21 millimeters a year. And then, so here's where we have that gap in the core. And so we're starting here. But for the modern Holocene, by the end, the erosion, as we're going from subalpine to montane to temperate, the erosion rates were 0.08 millimeters a year. So we go from 0.06 to 0.21 and back down again. And we have, I think this is probably the highest fidelity record out there for paleoerosion rates. So we have this opportunity to really watch them change in time as opposed to discrete sampling events on terraces. But I want to point out a few things to you before going back to that erosion rate data. And it's important to remember that with cosmogenic nuclides, they're insensitive to short-term fluctuations. You pretty much can't pick up changes of less than 1,000 years. And the integration time is a function of the erosion rate and the bulk density. And if you have transient conditions, your measured or apparent or derived erosion rates are always going to lag behind the actual or real erosion rates, because it's going to take some time for that signal to propagate, for the change in the concentration of nuclides to equilibrate. And so if you're in the modern Oregon Coast Range and your erosion rates are about 0.1 millimeters a year, it's going to take about 7,000 years for this signal to equilibrate. And if you were to increase the erosion rates by about 3 times, it's still going to take about 1,000 years for that signal to equilibrate. So if we go back to this, now I've plotted the inferred climate from the vegetation data. So you can see starting about 50,000 years ago, it's getting colder and colder. The climate is getting colder and colder. And of course we have this, oh, sorry, Bill, this increase in, you should cover your eyes. We have this increase in erosion rates. And one more way to think about this is if you go back to the classic climate curves for glacial and interglacial intervals, is that I'm showing you a starting point for the core that's about 50,000 years ago. But don't forget, it was cold and getting colder before that 50,000 year period. So the fact that we have these erosion rates that are climbing right from the start is probably a function of the fact that it was getting colder and colder and colder before that period. So there we are. I just want to reiterate that point that we had this, not only do we have an increase in erosion rates, but because we still don't know, so we have at least a 3 times apparent increase in erosion rates. So given the increase in erosion rates and a host of evidence from the core, including a profound change in the angularity and the size of the grain size distribution, and several other things, we expect that what's going on is frost weathering. So it's also called frost cracking, ice segregation. But this happens when you have temperatures of about -3 down to -15 degrees. You get thin films of water that migrate towards the ice front, and iceland's growth is vigorous, which leads to bedrock fracture and frost heave. Frost cracking or weathering is a function of both the mean annual temperature and the annual amplitude, and this is going to become important later on. It's really important to recognize that frost weathering is not the same thing as freeze-thaw, not the same thing as volumetric expansion of ice, which happens as you're fluctuating back and forth around that 0-degree temperature. So in this really fantastic set of field data from 2 years put together by Johnny Sanders. What you have here is ambient temperature. This is in a bergschrund in the Sierras. So you have ambient temperature here in the wavy line. I've put the frost cracking window on here for you. And then this is acoustic emission data at both near the lip of the bergschrund and further in. So I've got that backwards here. And what you can see is that the acoustic emission intensity is happening during the times of the predicted frost cracking window. So it's not happening at 0 degrees. It's happening when you have sustained cold temperatures. And so here's another way to think about this. This is a phase map diagram. This is a new frost cracking model developed by Alan Rempel, Josh Roaring, and myself. And this model is based on physically tuned parameters, things you can measure in the field, things like near frozen porosity and fracture toughness. And so here is the mean annual temperature on the x-axis, the y-axis is the annual amplitude. And this model predicts changes in porosity. So this is something I've had previous models. Of course, Bob Anderson has been a big proponent of this. We've had models that are a frost damage index. But changes in porosity are something that we can use as a community to think about weathering potential. And so ice-driven increases in porosity are a function, again, of that mean annual temperature and amplitude. And one of the things that I learned from Bart, the paleoclimatologist, is that it didn't just get colder in the glacial, but it got colder in the summers and much, much, much colder in the winters. So the seasonal amplitude increased greatly during glacial intervals. So even in unglaciated areas, you actually don't have to go down very much in temperature. As long as you have an increase in amplitude, your frost cracking potential increases greatly. So given what the evidence that it was frost cracking that was happening at Little Lake, we wanted to ask, what did that unglaciated Oregon Coast Range look like during the last glacial? So we downscaled all the available paleoclimate simulations from the last glacial maximum, so that's 21,000 years ago. We chose the best match based on the fossil data. So here's output for the paleoclimate models. Here's modern Little Lake in yellow, and this bright blue one is the one that most closely matches our analog site, which is the dashed line. And then we combined it with a frost cracking model. And before I take you to the results, I want to point out a few things using this washed out, at least from this angle, elevation map of the Oregon Coast Range. So it's important to understand what controls the temperature curves, because the temperature curve is going to control how long your piece of rock is in that frost cracking window. And what matters a lot is the topography, and not just the way we think of a mountain and environmental lapse rate, but what matters is things like relief and the size of the valleys. Latitude, of course, always matters, but during glacial intervals, proximity to the ice sheet matters a lot. And then, especially during periods when you do have very cold temperatures, how close you are to the buffering influence of a large water body like the Pacific matters. That will dampen the amplitude. So all these things matter for the shape of your temperature curve. And so here's the data. You just saw the topographic map. There's the Willamette Valley, this big flat spot here. So the panel next to it, the second one from the left, that's the mean annual temperature from the paleoclimate simulation 21,000 years ago. And what you can see is there's a 14-degree difference across the length from south to north of the Oregon Coast Range, even though it's only a couple hundred kilometers long. And the modern temperature difference is at most a couple degrees. So an extreme difference from south to north because of the influence of the ice sheet. Here's the influence of the ocean on the amplitude. So red is low amplitude, blue is high amplitude, and you can see how the amplitude increases as you move to the east. But you can also see that the amplitude isn't, it's varied in how it moves. So here you have the tip of the Willamette Valley that's being bounded by the mountains. That's just a really much higher amplitude, that basin nestling against the mountains there. And then on the far right is the frost. This is an older model, so it's not porosity, it's frost cracking intensity. And Little Lake is right here where that white dot is. So I forgot to mention this model was downscaled to 90 meters. So we're able to get, think about what's happening at the hill slope scale. So a couple things I want to point out. This gray area down here, that's the only part that the model does not predict frost cracking for. So here's this landscape that was never glaciated, but the model suggests that over 90% of the Oregon Coast Range experienced some form of frost cracking in this snapshot of time 21,000 years ago. Additionally, and this was a really big surprise to me when we first got the model results, is look how varied that is. I mean, if I would have been doing this without working with a paleoclimatologist, I just would have applied, said, tell me how much colder it was 21,000 years ago, and I'm just going to subtract that from the modern temperature, and then I'll model frost cracking across the landscape. And I bet you quite a few of you would have done that too. But Bart was like, oh my God, no, you cannot do that. What is wrong with you people? So after Bart and I had a conversation, this is the result. And it makes us confront that we have to think about that past climates operate on the landscape in different ways than they do today. So if we want to take this a little further and ask about the imprint of cold climes in the modern landscape, these are some fantastic Google Earth images that are supplementary to a paper by Gao. And what he's showing is under different conditions, depending upon the time of year that the satellite images were taken, you can see the signal of polygonal cracking in the Earth. And of course, polygonal cracking is a feature of permafrost periglacial landscapes. It happens at about -5 to -15 degrees, and these cracks can penetrate many meters into the bedrock. And just so you know where this is where the data was taken, and we're right here. So this polygonal cracking that was happening, that we can still see the imprint of in the landscape, happened not very far from where we are today. So if we want to think about where and how and to what degree do climate-driven changes influence critical zone processes, you can look at this spectacular Google Earth image provided by Dorothy Meritz, and you can see in these green hills the imprint of the old polygonal cracking. But of course, we can't always see it. There's a tremendous hidden legacy of past cold climes. There's places where there's fast erosion rates and the surface signal may be erased. Bioturbation does its turbation thing and the signal may be erased. And it's possible that the imprint is left below the surface and we can't see it in our eyes in the sky, all of the satellite data that's available to us now. And again, just to reiterate, because climate varied differently across the land in glacial times, we can't necessarily look at a place and say, oh, if it's cold here now, it must have been cold. I'm not saying this wrong. We can't necessarily look at a warm place and expect that it wasn't colder than the adjoining cold place in previous times. And so in the end, if we really want to think about the potential influence on modern surface and near-surface processes, we want to know where did this happen, how intense was it, and how deep. So this has led me to start to model at the continental scale. So this is really washed out from my image. I don't know if you can see it. But this is again, all of the available paleoclimate simulations from the CMIP5, PMIP5 models, combined with the frost cracking model. And in this case, I'm combining it with the newer frost cracking model. So what you're seeing on the color bar scale is from 0 to 0.84 millimeters a year. So this is the annual depth integrated calculation of change in porosity. And frankly, so modern is right here. I feel like, oh yeah, there's a model that says there's not much frost cracking. Well, that's the modern. This is the ensemble. This is the average of all the models, and all the other maps are the individual model output. And I don't care which model you pick. You can take your choice. They all suggest that significant swaths of land in unglaciated North America were susceptible to frost cracking. Now, there's 1,000 caveats, right? It depends upon if the bedrock is near the surface. It depends upon if there's snow cover. I'm sure for every caveat I have, you can come up with 10 more. But you can't get away from the fact that every single paleoclimate model suggests that broad swaths of North America had sufficient temperature conditions for frosty processes. And don't forget, I'm focusing on frost cracking, but you can think about things like solifluction and how that might speed up sediment transport. There's all sorts of things you can think about that these models suggest we might need to think about. And so this is a really simple summary slide. There's no intensity on here. All that this is showing is in green is the extent of modern frost weathering. in North America of any amount. And then the blue is showing from the ensemble model, the average of all the paleoclimate simulations, the predicted extent of frost cracking across North America. And then we can start to ask other questions like how deep? Because, of course, it doesn't just matter where and how much. If we want to know how it's influencing places, for example, where the erosion rates are slow and you might not have completely removed the frost-shattered subsurface architecture of the critical zone. So this is a subset of the models, and it's going from, this is the median frost weathering depth, and I'll show you what I mean by that in a minute. So it goes from 0 on the bottom, the darkest blue is 2.17, and so here's some frost cracking intensity curves. This is an annual change in porosity in millimeters. And so this is at -5 degrees. These are all at the same amplitude of 10 degrees amplitude. -5 degrees, 0 degrees C, and 5. And so something like this would be the median of the frost cracking depth. Here would be the median of the frost cracking depth. And here would be the median. And so you can see that, especially when you begin to think about how amplitude matters so much to both the frost cracking intensity and how deep. So this right here is a plot of that medium depth, and there's a sweet spot here. So at about 5 degrees, -5 degrees C, you don't have to have very high amplitudes for there to be frost weathering. And then it's about -3 degrees C, -3. So you can begin to think about places on the continents that would have been in this window where we might expect to still see the signature of enhanced weathering in the subsurface. And so I really began to wonder, those were snapshots in time. And snapshots are a little unsatisfying, and I really wanted to think about trends through time. And I've been really just amplitude. The amplitude is really what matters in the end. And so I went to my new paleoclimate colleague, Song Feng, and his graduate student, Cheng Lu, at University of Arkansas, and I said, what can we do to produce some time series of amplitudes, some downscaled time series? So this is for, again, continental North America, where the ice sheet wasn't. It's ignoring the very edges of the right against the ocean on the west and east and south coast. And this is from the TRACE model. And what you have here is the black line is the annual amplitude, and the blue line is the mean annual temperature. The axis on your left is annual temperature. The axis on the right is the amplitude. And what you can see, and this was a real surprise to both Song and I, is here's the last glacial, and here it is where it starts to warm at about 18,000 years ago, and temperatures are warming. Amplitude is increasing, not decreasing. So even though it was getting warmer as we came out of the glacial, there were still places where conditions were likely sufficient to continue to have frost cracking, because we have this rise in amplitude. And then when you hit 13,000 years, when we switch from marine isotope stage 2 to marine isotope stage 1, that's when you finally have your amplitude begin to marry. The increase in temperature has the decrease in amplitude. And we are right now exploring some paleoclimate models that go further back in time, because to see what we can do, what we can find from it. So again, we have this potential, because amplitude matters as much as mean annual temperature, we have this potential of having a frost cracking, frost weathering that is imprinting on modern processes. So this is my halfway summary point. And what I'd like to say is that frost-driven sediment production was pervasive during the last glacial maximum in mid-latitude terrain. It can be significant in unglaciated settings despite the lack of an obvious or diagnostic topographic signature. This suggests a reevaluation of steady state in soil mantled landscapes. I'd like to suggest it may be steering modern processes, and cold intervals with vigorous frost processes perhaps are the pace setters of landscape evolution, even in unglaciated terrain. And I have one more point I want to make on that, and that's I really think that we are moving with this combination of available geophysics, of paleoclimate simulations, of having models that we can physically tune. We're moving towards a combination of theoretical and field data through time at the landscape scale, such that we can actually begin to think about how the subsurface architecture, or perhaps if you're interested in how large blocks might buffer the bed of a river. But we can really begin, we're poised, I think we're really poised to begin to think about this systematically through time. And so I find this to be incredibly exciting, and I hope that many of you will join in thinking about this. And then the trees. Now it's time to move to the warm things, right? So what of the warmer forested landscapes? Is it possible to develop a biomechanistic soil production function that we can use to predict soil thickness through time? Well, again, this is a lot of people. And actually, I realized as I was putting this talk together that my interest in this goes back to when I was doing my master's with Leonard Sklar and digging a lot of pits. Anyone who works with me knows that there's going to be some pit digging involved. And so Leonard and then Cliff and I spent a tremendous amount of time in the field, and he shaped my thinking in so many ways. Josh Roaring, again, shout out to him. Greg, so I should probably going a little bit out of order on this, but I've been working with the team at Boulder Creek, and Greg Tucker, there's probably not anyone better, except maybe Bob Anderson, or maybe they're equal, to sit and talk how we might model this stuff. And Missy Epps, she and I have been doing a lot of work talking about the cracking of rock. Danielle, all of the CZO crew has been so instrumental, having a large group of people to work with that are critical zone scientists and not specific disciplinary scientists. So Daniela Rempe and Jesse Hahn. Todd Dawson is, for those of you who don't know him, he's an integrative biologist. He is there with all his fame and fortune telling me what type of tree that is, an oak. Bob and Suzanne Anderson, they are feeling the wind in the trees in that picture. Bob saying, I feel it, how about you? And then, of course, the guy in the pink hat, Bill Dietrich. So all these people are part of this project, whether they like it or not. So I was talking about this with Leonard the other day, and I'm going to sweep through a bunch of stuff, and I'm going to start out talking the big scale conceptual models, but there's a lot of challenges involved. There's a reason that nobody has really tried to tackle this. I cried my first year and a half of my postdoc. And then I'm going to talk about cracking open the box a little bit. So there's going to be a bit of a nested set of things here. We'll go big and then go increasingly small and then maybe come back big. So I'm going to give a rapid overview of critical zones and soil production and the role of trees in an uplifting, eroding world. So importantly, I'm not focusing on the flat places so much. And then I'm going to talk about if trees are drivers of bedrock to soil conversion, what don't we know, what do we know, and what might we need to reevaluate. And then finally, I'll be presenting some new results, cracking open the black box of soil production mechanisms and ways we can quantify the magnitude and frequency of forces that damage and detach bedrock. Okay, so if we want to take a geomorphic long view of landscape evolution, and here are some of my fabulous graphic skills again, so you're seeing them in both parts of the talk. So as you know, in the geomorphic long view, as the rock is being uplifted up into the zone of water and life, And of course, as this rock is coming up, it's already carrying with it tectonic damage. It's carrying its own lithologic fabric. It might be carrying the topographic stresses that further damage the rock. And as it comes up at some point and meets water and life, mainly chemical things begin to attack it and break the rock down, weather it. And at some point on its transit upward, as material is being removed from above, the rock begins to encounter things that make it strain. And at some point, the material is detached and rotated in space. And thus, that immobile rock becomes mobile. And by that, for people, it does not mean that the rock came from far away. It just means that it's no longer attached. The fabric is gone. It's rotated in space. And of course, these three surfaces that I've just described to you, the mobile material surface, which I'm going to call ZS, the top of the weathered rock, which I'll call ZW, and then the top of the fresh bedrock, 3B, ZB, What's so amazing about these is that they co-evolve. You can't think about them as a single layer. These are layers that co-evolve in space and time, such that any change in the weathering, in the mechanisms that drive uplift or weathering or transport are going to have implications for how landscapes evolve. But the problem is, when we're talking about what sets this layer, this thickness, this boundary layer in between the mobile material and the immobile material, we don't yet know. We can't predict through time what sets that thickness. And so we can go to, for many of you, the familiar, I just described, this is the same conceptual model developed by Heimstedt et al. And so many others, where you have in this cross-section here, here's ZB, the bedrock, there's that weathered zone, that interface in between the weathered rock and the sediment above with sediment transport. And of course, this is the P term, is that bedrock detachment, right? That converting rock into soil at some rate that we can associate with some depth. And as encapsulated in this cartoon, the pace of, and in this first equation, I think it's one of Bill's favorite equations. Would you have a favorite equation, Bill?
I like it.
Okay. So as encapsulated in this, it's the pace of divergent sediment transfer versus the pace of soil production is what controls sediment depth. And of course, below it, we have our classic landscape conservation of mass equation. And as you all know, there's that P term that we still we don't have a mechanistic formulation. We don't have a way of predicting how, if things change through time, that P might change. And we have conceptual and empirical models that we work with. We have the familiar hump function, first posited by G.K. Gilbert. I need to hold up my mug to him. The rate of soil production depends upon soil depth. And of course, there's some sweet spot, right? Where if it gets too deep, you can't attack things. And if it gets too shallow, then you don't have enough material to attack. And then there's the exponential function, which suggests that disturbances and fluid migration less frequently affect bedrock as soil thickens. And we can make equations for these. And this course term on the right, when this goes to 1, we're at the exponential function. So you can flip back and forth in between exponential and hump function. But we don't have, there's no mechanics in here. There's nothing about the landscape. It's just an equation that describes the way we think landscapes work and that data has shown they work. So this is a compilation by Dixon and Rebe showing erosion rate data. Now we can measure soil production rates. We can measure them everywhere, thanks to the advent of cosmogenic nuclids. But the thing is, so what they've compiled here is all the black dots are erosion rate data that suggests a soil production function. All the white dots, there's no clear soil production function. So we can measure the heck out of this stuff. But, we still don't have a way of saying what controls it, especially through time as conditions change. So if we start out considering two end members, and in scenario 1 over here on your left, the thickness of soil is much, much greater than the thickness of the immobile material. And in scenario 2, this cartoon on the right, the thickness of soil is about equal to the thickness of mobile and immobile weathered material. In scenario 1, trees primarily shape the critical zone through biogeochemical reactions in the weathered zone. The roots don't touch rock, so they're not going to convert that rock into soil by physical weathering mechanisms. But in scenario 2, we expect that tree processes set soil thickness, that roots and the associated fungi facilitate hydrologic uptake from fractures and nutrient acquisition, and that there's a significant physical weathering and detachment component. And for the rest of the talk, this is the scenario I'm going to be focusing on. And I have to add a little aside. I'm going to talk about physical weathering mechanisms. That doesn't mean that I don't acknowledge and love all of the potential chemical weathering mechanisms. But for this talk, I'm just going to focus on the physical. So if we want to start and ask what controls the thickness of soil, well, in places, now we're getting to the part of what we don't know, just to give you a map here. In places where we expect that tree-driven mechanisms play a significant role in damaging rock and turning rock into soil, well, what are the mechanisms? What role do fractures and fracture density and rock strength play in root-driven water weakening of rock and the generation of mold material? And do mechanisms, frequency, or magnitude vary with species, forest structure, climate, aspect? Pick your poison. So I'm going to highlight for you a couple of the great cross-disciplinary unknowns. So the first one is we know that roots hydraulically redistribute water. So if the upper part of the soil or the rock is dry, the roots that are in the water, for example, at the Eel River critical zone, they take that water, the rock moisture that's there, and they pull it up and provide water to the upper roots. We also know that water weakens fracture crack tips. Rock breaks easier when there's water involved. And that crack tip propagation rates are a function of the crack tip length. The longer the crack tip is, the faster that crack tip is going to propagate. So there's an important place here in between the work that biologists are doing and that groundwater hydrologists are doing and that people like me are doing and rock mechanicians to try and understand what role water availability and hydraulic redistribution play in enhancing crack tip propagation. And then we know from the work of many, many soil scientists that root distributions decline exponentially with depth. But here's what we don't know. We don't know if root phenology changes in rock. We don't know if there's structural control. So if you have a certain fracture pattern, does that mean that some trees can adapt to that fracture pattern and change the very architecture of the roots and others can't? We don't know how water availability controls root phenology. And again, I just mentioned those species limitations. So there's questions here about feedbacks between above-ground forcings, such as water and wind, and how that shapes the coevolution of forest structure and the soil-rock boundary. So there is a picture of tree throw for someone who's never hiked in the forest and seen a tree liberate rock. And these are some of the things that we know. We know that rock properties, things like strength or fracture density, control the damage that a root can impart to bedrock. We know that fracture density and shape factors and aperture sizes will control rooting density and potentially limit root size. And that root size correlates with root growth pressures, and that root density declines with depth, and that tree throw can convert meters of immobile to mobile material in a moment when that tree goes over if the roots are embedded in rock. So All of this just suggests that there's multiple mechanisms that may contribute to rates of bedrock detachment, and these mechanisms are controlled by rock properties, which I consider to be soil production inhibitors, and the tree root density, size, and water availability, which we can think of as soil production facilitators. And so in this spectacular LiDAR image here from the Oregon Coast Range, these bumps that you see across the landscape, those are not an artifact of the LiDAR processing. Those are the very signature of the tree roots digging into the bedrock and breaking it up, and when they turn over, creating a pit and mound topography. And we can quantify this, and we did. So this is for the Oregon Coast Range, and what you have on the y-axis here is the roughness. It's the curvature measured over different length scales, and there's the length scale on the x-axis. And what you can see is there's a scale break here at about 7.5 meters, and we consider that to be the scale break that distinguishes the wavelengths of tree and pit mound features and smaller disturbances on the landscape, and the ridge and valleys. So in the Oregon Coast Range, the pit and mound features from tree turnover roughen the surface at short length scales. But not all places in the Oregon Coast Range. And so this is what I like to call tree-hating rock. As you can see, there's not a tree growing on it. This is not a landslide surface. There are solution pits on this rock. This is rock that is the exact same lithology as the Tyee, and I'll show you pictures of the normal Tyee in a moment. But this rock, in the Oregon Coast Range, it's so amazing. You can grow a Douglas fir in 20 centimeters of soil because they're bedded turbidite deposits, and the roots can get in under those turbidite deposits. But it turns out this tree-hating rock is about 2.5 times stronger than the typical Tyee. It's because of a very, very, very minor diagenetic clay that we think makes the rock stronger. So not a weathering clay. It's from the burial process. But here's the difference. So here's that tree-hating rock. Here's the typical Tyee. And you can see the difference in the fracture density. So the Tyee fracture density is about 0.5 to 1 meter, where the resistant rock fracture density is 10 meters. And thanks to LiDAR, of course, we can quantify what the eye can see. So these are just transects across the land in the raw LiDAR. And so you're just looking at the roughness. So the top is in the soil mantle landscape, and this is in the tree-hating landscape. And then just applying spectral analysis to that, this peak here, the spectral peak, that's the root roughening, and that's at 7 meters. And then here is the 10-meter peak. Here is the fracture spacing. So what that leads to, if you can start to think about, well, how small does a block have to be before it can get lifted by a tree? And I'm not going to walk you through the calculations, which are really simple, but it's just basically, if we're really conservative, instead of saying we have a 10-meter block, let's make it a 3-meter by 1 meter by 1 meter block. And if you calculate the lift forces for a tree root to be able to lift that block, it would have to be about 0.8 meters in diameter. That's not a tree you find anywhere. So this suggests that fracture spacing, or potentially, material mass, I don't know what I meant. Oh, how dense it is, sorry. Maybe a first order control on tree-driven rock-to-soil production mechanisms. And so if we start to dig into the literature for what we might need to reevaluate as a community, I mentioned that root densities decline with depth in soil, and that root size correlates with root growth pressures. So what you see here on left, this is one of the few studies I know that did this. This was done in Southern Oregon. And I'm going to mispronounce his name, so apologies if he's here, and I do. Swinecki and Newton, they dynamited cliff faces. I can't wait to replicate this study. So they dynamited cliff faces, and they carefully measured the coarse and fine roots in the fractures. And so you have at the top Manzanita and Ponderosa, and these bottom two plots are mixed Doug fir and madrone. The soil I've highlighted for you in orange here, and then on the left side of these plots, the yellow here, which I can't see from here if you can see, but you can see that short of this plot here, that the roots growing, the coarse roots growing in the rock do not at all suggest an exponential decline with depth. So the fracture spacing and where the trees can grow is going to control what the root distribution looks like. And so I think as a community, when we think about how trees break rock up, we need to reevaluate how we think about it. And then briefly, this idea that root size correlates with root growth pressure. So root growth is often invoked for a way that you can break rock. Mighty roots that are just pushing the rock out of the way, right? And this is a compilation of all of the available root growth pressure data. So root growth pressures are here, root growth strength, it's in megapascals. And then this is the root diameter. And you can see that there's a nice relationship, that as there's axial forces, the tip of a root is about usually a third higher than the radial forces this way. But you can make really nice equations and show how much you might expect from the radial forces. But here's the problem with that. All of the root data that has ever been used is collected on roots that are 25 millimeters or smaller. And they're often done in experiments that involve things like glass beads. It makes sense if you're an agricultural scientist and want to know what's the stiffest soil you can plant your cotton in. But it suggests that we really, I'm going to move to the next slide, I'll make this point further, but the last thing is that it's also really important that roots can fantastically change their shape when they want to get in rock. So these are two photos. Martin Hurst and I were out hiking around in the hills of Scotland last summer, and this is a root, and you can see it just go totally flat to dive into that rock. And you can see this root here doing that same thing. So we start to think about what we see in soil and what we think about root size and distributions. It's not necessarily the same thing when a root is searching for water and nutrients when it tries to dive into rock. So coming back to that bit about not using things like root growth forces from the literature for what we're doing, I would just really like to encourage us as a community to start thinking much more in terms of rock mechanics and thinking about crack tip propagation. Because that's really, when you think about a root like this or a trunk growing into rock, what is way more likely happening than these growth pressures. And I'm going to come back to that in the end. So tree throw. I want to briefly touch on tree throw. Charismatic tree throw is wonderful. As I mentioned, you go hiking and you see how you've instantly converted rock into soil. And in this wonderful model put together by Manny Gabay and Simon Mudd, what they suggest is that if you combine the thickness of the weathered immobile material that the trees get to, so what they can get to, and the tree density, that those two things combined are what give you a humped function. But here's the thing. Tree throw can be rare in many forested settings. All trees, however, insert a large portion of their mass below the ground. And what I'm going to suggest to you with the next few slides is that trees do not have to fall over to detach rock and make it mobile. And what you have here right, this is Ground Penetrating Radar by Roaring et al. And this is the Coast Range, of course, so the trees are clear-cut. They like to clear-cut the trees there. But these are the stumps of what once were formerly magnificent Doug firs. And you can see this is the transformed GPR, and you can see there sure is a correspondence of broken rock below those big trees. So here's some hypothesized tree-driven rock damage and soil production mechanisms. You could probably come up with a few more, and let's chat. There's wedging, and I forgot to, this is a photo that Greg Stocks sent me. There's, of course, tree throw. And these are the things the visible have, right? You can walk around and see it. It's charismatic. And then we have things like growth pressures that I just talked about, wind-driven tree sway. And I'm going to talk a little bit about root swelling due to water uptake, which is something that Todd Dawson, the integrative biologist, and I started hypothesizing when we first got together a couple years ago. So daily, at night, when the sun goes down, trees take in water through their roots. And then when the sun comes up, their stomata open, and there's an instant signal to the tree, a near instant, and their capillaries shrink, and they send water up to the top. And then at night they swell, and during the day they shrink. At night they swell, and the day they shrink. So we both hypothesized that perhaps this swelling and shrinking might impart enough of a small force over cyclic forces, over the lifetime of a tree. You can get 10,000 taps in. Or if that tree dies, another tree is going to occupy that crack. So there was the possibility of imparting very small microcracks. But if you tap a material enough times, those microcracks coalesce. And you can significantly reduce the tensile strength of that material. So that was one of our other potential hypothesized tree-driven rock and soil production mechanisms. So off I went to go work on this problem at a couple critical zone observatories. And this is a LiDAR-derived image by Colin Bodie of the spectacular forested Eel River Critical Zone Observatory. And I want to point out a couple things here. This is not just a dense old-growth forest, but the species assemblage and canopy structure, and thus wind, varies with aspect here. So the north-facing slopes, you can see just how rough the tree canopy structure is. So the wind here is very turbulent. Compared to the south-facing side, you have, rather than a predominance of Doug fir, on the south-facing side you have madronan oak. You have heliotrophic species. You have species that grow towards the sun. So rather than going straight upright, they fill in the gaps. And what you end up with is a forest that looks like someone's crew cut. So the wind can just pass right over it, compared to an old-growth forest with its many different tree heights. And then this is the Boulder Creek CZO. It's a totally different looking place. And here we have mainly ponderosa pine on the south-facing slope, and you can see the difference in the tree spacing. And what we have at the Boulder Creek CZO is we have wintertime monsoon westerlies. That wind just comes and blows and blows and blows from west to east. And so to tease out the mechanisms and frequency and magnitude, I've used little force sensors. They're not at all designed for what I use them for, and they are really tiny. So this is a pencil tip. There's the force sensor. They'll measure anything from about a tap to 1,000 pounds or 4.5 kilonewtons of force. And I insert them at that root rock boundary, and they're really great because almost anything else you could use from the geotechnical world will destroy the very thing we're trying to measure. And then because I'm working I have accelerometers at the base of the trees, we have anemometers, and because I'm working at critical zone observatories, I have all of the wonderful infrastructure, including data on precipitation and shortwave radiation. Now, I do have to say, these sensors are not the best, so I'm gonna have to walk you through a little bit of the data, because while they have temporally behaved fabulously, they correspond with the signals of wind and precipitation like a champ. Some of them are still going 2 years after installation. But they don't respond well to be getting slammed a lot by big trees, and so that we can't, the resistance base and the resistance drifts in ways that we can't back out. So I'm working with John Selker of OSU. We're trying to design some brand new sensors to tackle this problem because they need to be tiny, they need to be robust, and they need to measure dynamic and static forces over really large ranges. So when you see the data, sometimes I only plot the resistance because I can't trust the force data. But the resistance is still giving us a signal. And resistance goes down when forces go up. So I've tried to mark this on all the plots. You'll see an up arrow telling you the forces are going up. Okay, so this is some data from the Eel Creek CZO. This is Treebeard. And Treebeard is a magnificent old-growth Doug fir. It's 65 meters tall. It's a big tree. Sits right on a ridge, right where it can catch all the wind. And let me show you some of the data from this magnificent tree. So what you have here on the bottom, this is from a winter storm over a couple days. This is the average wind speed. These are the gusts. And this is that resistance data the sensor saturates. I mean, this tree is probably 20,000 kilograms at a minimum above ground. So the sensor can't handle that. But what I want you to see is that when the wind blows, when we get really big gusts, about over 7 meters a second, Treebeard is rocking back and forth with the wind. I have a sensor planted at the base of the trunk on the rock. And that tree is moving back and forth with the wind, that massive tree. But here's the thing. We don't get those big wind events very often. And observations, so when I've been out there, what I've noticed is that all the big trees, bigger than about 100 centimeters, there's significant fracture in the surface, rock bounding, in the rock bounding the massive trees. So it's like broken tile. I might have to move broken tile to get to intact rock to be able to plant my sensors. And one of the questions that's worth asking, and Josh started asking this a while ago, is will commercial forestry and forest loss of big trees like this via climate change minimize this critical zone shaping mechanism? And let me show you what I mean. So here's some data, it's a compilation from several different groups, and the top is the volume of detached bedrock. The middle one is the large root biomass, and the bottom one is age versus diameter breast height, which so oftentimes you can use the diameter breast height of a tree to back out what the age is. And I want you to notice is you really do not get any significant material that is detached until the trees are about 70 years old. So as we move towards commercial forestry that's growing trees that are growing them to 40 years old and cutting them, we have to ask if we're beginning to eliminate this important soil production mechanism. Okay, so this is some data from Colorado, and here you can see I'm just using the resistance, so the force is pointing up this way, the wind is on the top, resistance is on the bottom. There's the wind, there's the instrumented tree, so this is the westerly wind that just blows against that tree, and they just walk hand in hand. When the wind blows, the tree is just pressing on the rock, and then the wind blows, the tree is pressing on the rock. And even the little tiny times when the wind, just these little gusts, you can see it pressing on the rock. So this is the way a stiff ponderosa pine behaves. And now if we travel back to the Eel River Critical Zone Observatory, and this is a small tan oak that has an accelerometer at the base, and you can see some of the force sensors there also diving into the rock. They did not survive the storm, so I cannot use any of the force sensor data, but I have wind data from, there's Treebeard right in the back there, so I have wind data from the anemometer at the top of Treebeard. And so these plots on the left are from the accelerometer data. It's the X, Y, and Z. So when you see the data spiking in all three X, Y, Z directions, you know that the tree is doing this at the base. So here's the data. Here's a wind event. I mean, there's a movement in all three directions. This is very washed out, but if you can't see it, right here is a wind event. Here's the thing, the wind event keeps going. The tree is stopped. Here's another wind event. And it keeps going, but the tree has stopped. And this repeats on and on. And here's what's happening, I think, is trees can act as load dampeners. So everyone teases me when I talk about this, but I can't do it without waving my hands. I'm a big hand waver, as many people know. So if you have a big oak, a big, broad canopy tree, and the wind hits it, all of the branches start to move with slightly different timing. And as they move, those waves come back and they coalesce at the top of the tree, down the stem, and you get destructive interference or mass dampening. So the tree is protecting itself. I'm amorphizing, but this is what the tree does. This is one way that trees that have really big canopies don't fall down. They have this self-dampening behavior. So even though you see the top of the tree doing this in the wind, it's not doing much of anything down here. And so this is a fabulous data set from James et al. And this is for a conifer and then a big canopy tree, and they put strain meters on the tree. So this is what you're seeing here, is them tracking, not at the base like where I did it, further up the trunk, but they're tracking the movement of that tree trunk. And then, as you can see, the conifer, in this case, has 2 peaks, and the broadleaf tree has 1. And they see this, they do this for many, many different tree species, and they show that depending upon the canopy structure, trees are either self-dampening or not. So you can begin to ask questions about how different species, as species change, either due to changes in climate or lithology, how the frequency and magnitude of the wind events might be felt below the earth. And the other thing I'm not showing here, but there's just quite a bit of literature in the botany literature that trees also, when it rains, when they take up water, their mass changes, and so their response to wind changes. So water availability begins to matter a lot. This is a stiff madrone in the coast, back in the Eel River, and we expected this to behave just like that live oak. They have big, giant canopies. But here you can see, here's the accelerometer data on top, again in the XYZ. And here we have the force sensor data and the wind data. And you can see that it behaves much more like those ponderosa pines, which begins to suggest wood properties also matter, how stiff or bendy a tree is. Okay, so I'm almost done with the data that we've got. This is the shortwave radiation. This is the stuff that, this is what Todd and I hypothesized on these very small forces that we might be able to see on the rock itself. So here's the root data. I actually do have a force number here because we just planted the sensor and it was not yet destroyed by the wind. And so what we have here is the blue is the shortwave radiation, the green are the forces. That's nighttime. No solar radiation at all, and you can see the forces go up. Again, you can see there's nighttime, the forces go up. So at night, you can see this root tapping on the rock at this 0.02 megapascal. There's the daytime, and you can see when you have the daytime peaks in the shortwave radiation, the forces go down. And then these little spikes, I didn't put the plot up here, but they correspond beautifully with rain events. So the roots plump when it rains. It turns out they can't hold the water all the time, so the timing of the rain matters as much as the total amount. Okay, this is so preliminary data that I worry about showing it. This is like just last week, and let me walk you through what we're seeing here. What I forgot to put on was the legend. So let me tell you what we did, and then I'll tell you about the legend and what the results are. And I'm super curious if anyone else has some ideas about what's going on. So, because we measured those small forces on the rock, and I had a universal testing machine in my lab, I said, let's do a physical experiment. So Jacob Klein, my wonderful undergrad, who is looking for a graduate for a PhD doing hydrology, we set up a series of experiments to tap the rock using the same values normalized for the size of the disk as we had seen in the tree. So we collected rock from the eel. This is the sandstone. We cored it out. We put it through the CT scanner so we could get high-resolution 3D imagery of the rock structure before we tapped it, and then he tapped it 10,000 times. He didn't tap it, he had a controller. But 10,000 times at very, very small values. Then we put it back through the scanner again. So what you're seeing here, the yellow dots are the porosity, the void spaces in the rock. This is a 3D image of a 1-inch cube, okay? And then this is after tapping. And much to our surprise, there was a change in the void volume size in this rock. And you can see this in the histogram. The blue is the before, the pore volume, and the yellow is the after. Now, I don't know if this is an artifact of experimental design or if this is real. But if it's real, it sure suggests the potential for trees to begin to modify the weathering potential of rock just by increasing the volume of the voids in the rock with these little taps. So I'm happy if anyone has any ideas on this. We can't tell if there was expansion, if there was volumetric strain, because we have scanning artifacts from the CT scanner, so we can't go to the edges and see if this actually increased in size, but there's a lot more experiments to follow on this now. So here's a quick summary of what we know, what we might want to reevaluate. Wind response may depend on tree size, stiff versus bendy, water availability, and canopy forest or structure. Diurnal fluctuations in root forces have the potential to increase pore size or impart a cyclic stress fatigue over the lifetime of a tree and thus considerably weaken the enfolding rock. Precipitation generates tree-induced forces on bedrock. Measured growth forces, I don't measure them. There's no background force, and which makes sense because really if you think about if the wind can push a tree, you're more likely to have a crack tip propagation and open up space for the tree to continue to grow compared to just having tree roots that are pushing the rock apart. And then finally, tree throw may matter less as a soil production mechanism that our models suggest. And I'm wrapping up right here, and I just want to say, you know, am I anywhere near our soil production function? No. But we can start to think about frequency and magnitude, I think, and think about how we can model probability distribution functions to take this to a more landscape scale. And with that, I'm going to come back to Luna's quote, and which resonates so strongly with me, and just summarize by saying these projects are the result of an admixture of disciplines that allowed for new ways of asking old questions, and in my opinion, the path forward to quantifying the mechanisms that shape the Earth in order to develop new geomorphic laws likely dictates crossing traditional disciplinary boundaries. And with that, thank you very much.
It is 6 o'clock, but we, yes it is, you look at your watch.
I timed it perfectly.
Are there any questions that might be burning before we let you go? Because probably some of you have to go someplace. Anybody would like to step forward, take a minute or two? Anybody? I think people are leaving, so we better hurry. Not only recall that she's both the Leopold Awardee and the Sharp Lecturer, so she gets 2 of these. So congratulations. Thank you, Jill. And thank you for a wonderful presentation, and thank you all for coming, and we'll see some of you at the reception.
And bourbon's on me.
Bourbon's on her? What? Okay, thank you.